Today we will be talking about Kirchhoffs Laws, which are laws that demonstrate the conservation of charge and energy, and we will be applying them to circuit diagrams to help us solve those more complicated problems. The first one is the junction rule. The junction rule states that the sum of all currents entering a junction is equal to the sum of all currents leaving a junction. For me, this is best understood when I consider the analogy of current and water flowing through a pipe. If we had water that was flowing in a pipe and it came to a junction, you can imagine that some of the water would go up and some of the water would go down in this current analogy. But if this pipe eventually came back together, the water would be equal at the beginning and at the end. We do not have more water here or here. Water was not added nor taken away in any of these points. And that's the same with current. When we have current flowing in a circuit diagram and we come to a junction, we still have the same total amount of current when we come to that junction. However, some of it will go in one direction and some will go in another. So if we called this I1, we now have I2 and I3, which add up to I1. So if I1 was 10 amps, I2, let's just arbitrarily say, is 6 amps. How much current is in I3? We know that it would be 4 amps, because I3 plus I2 equals I1. This can be written in this equation, which will be used later. So let's go to a little bit more of a complex circuit diagram. Let's say we still had our same 10 amp current that's flowing in this direction. Then we come to a junction. This doesn't exactly look like the junction we had before. It's in different directions, but does that matter? It doesn't. There will be some that goes in this direction and some that goes in that direction. So if we arbitrarily say this was 6 amps, how much current flows across this segment? It would be 4 amps. Now, it's not actually arbitrary how much current is going in each direction. These squiggly lines are resistors, and that is the key to determining how much current is flowing in each direction. If we go back to our water pipe analogy, if we have water flowing in this pipe, but at the junction, one pipe is larger than the other, you can imagine that more water would flow in the pipe that was larger because there's less resistance. It's easier. More water can easily flow through that pipe. And it's similar here. If we have water or charge that's coming here, it will choose the path of least resistance. So if this has less resistance, more of the charge or more of the water in this analogy would flow through this portion, meaning that 6 amps of this current is going in that direction and 4 amps of this current is going in that direction. And that is simply because of the resistance that is indicated here. Now, these laws hold true no matter how many branches you have. If we had a branching system that looks something like this, it's easy to say that we had current coming in, but what do these currents equal? Well, they equal the sum. The sum of this current equals the current that came in. And it's the same if you had a bunch of currents coming in to one segment. The sum of these currents would also equal this current. So let's use this information and remember it as we go on to our next section, the loop rule. So the loop rule states that the algebraic sum of changes in potential around any closed circuit path must be 0. What does that mean? Let's start with the closed circuit path. If we have a closed circuit path with a voltage here, it says that the changes in potential are going to equal 0 by the time we get back to the beginning. So where is this energy going? If we believe in this conservation of energy, that energy is not created or destroyed, we look again to these resistors. Ohm's law, which says V equals R times I, explains that when we have a voltage and a current that's passing through this resistor, we will have a voltage drop. And so what is this voltage drop? Well, if we apply Ohm's law to each of these resistors, we will be able to calculate exactly how much voltage is lost at each resistor, and it will eventually equal 0. In other words, the EMF at the bottom that is producing this voltage minus the voltage drop at resistor 1 minus the voltage drop at resistor 2 is going to equal 0. Let's break these down a little bit further to be resistor 1 times the current and resistor 2 times the current. With this equation, we'd be able to solve a more complex circuit diagram. Let's give it a try. Let's say we were given a problem in which we had a circuit diagram with two voltage sources, one at 15 volts and one at 20 volts. Let's further say that this circuit was divided in the middle and had a resistor of 250 ohms and had one more resistor over here of 125 ohms. And now the problem wants us to determine the current that is flowing in each segment of this circuit diagram. How do we solve this? Well, for me it's easiest if we start with the junction rule. We will start by assigning our current 1, 2, and 3 to the different segments and determining the current that's coming in and out of each of the junctions. So if we arbitrarily start at one of these voltage sources, let's go in a clockwise direction. The direction doesn't really matter, but for me it's easy to remember clockwise. And we get to a junction. We will put a mark there to remember that that's a junction. We're going to continue in the clockwise direction. We get to an EMF. That doesn't count as a junction, so we'll continue. Then we get to another junction. We're going to put a dot to remember, and we'll continue around. Now we've traced the perimeter, but there's one segment in the middle. Again, we need another arrow indicating a current, and it doesn't matter which direction this goes. That is because at the end, if we have a positive or a negative current, it will indicate the direction of the arrow was either right or wrong, and we'll address that at the end. So for now, I'm going to put it pointing downwards. Now we need to label each of these arrows. As you can see, there's one arrow that goes here, one arrow here, and one here. For me, I just continue in that clockwise method, so I call this I1, let's call this one I2, and this one I3. And so at this junction, let's establish the equation. What is coming in? We have one current going in, which is I1, and we have two currents that are leaving, I2 and I3. This just happens to be similar to the equation that we wrote before. That was just happenstance. You'll end up with some that are different, and that's okay. The equations still work. So let's continue. We have one other junction to assign. The current's coming in. We have I2 that's coming in, and we have I3 that's coming in. So we'd write I2 plus I3. And which currents are leaving? Just I1, as you can see here. So we'll write I1 on that side of the equation. Now if you notice, this equation is the same as that equation. And so we only need to keep one of them, for they are the same. And we're going to write it over here to remember it. Thankfully, we already have it written down. And I will erase these to keep the board a little bit more clean and simple. Next, we are going to write the loop rule for each side of this loop. So we're going to start here in the corner, and arbitrarily we're going to go in a clockwise direction just to keep things orderly. But we're going to determine, as it says, the voltage drops across each segment so that the closed circuit equals 0. So starting here, this segment has no voltage drops, and that's because there's no resistors and there's no EMFs, so we don't have to worry about that segment. We go down this segment, we find a resistor. This means that we need to assign a voltage drop because the current is going in the same direction as the resistor. So we'll indicate a voltage drop by a negative sign, and then we'll harken back to Ohm's law, which is V equals R times I, as we talked about earlier. So the voltage drop will equal the resistance times the current. So 250 I3 in that segment. Let's continue around. This segment doesn't have any voltage drop. Now we come to this segment with the EMF. This EMF, we're passing through on the negative side to the positive side, which is indicated by the length of these lines. it is 15 volts, and because we're going from negative to positive, we will get a positive EMF, or plus 15 volts. We continue up, and now we're at our starting point, and as we indicated earlier, our starting point must be 0. So now we can algebraically solve this for current 3, and that's because we only have one unknown. So now we know that I3 is equal to 0.06, which we can write on the board over here to remember that number. But I'm going to erase this portion of the board so that we can keep it clean. Now we're going to do this side. Let's continue across the top. We find a voltage drop because we are going across a resistor with the current, so we'll indicate that with the negative sign. And again, we'll use our times I and do 125, which is the resistor times the current of I2. We then get down to an EMF. Do we add the 20 volts? Not in this case. In this case, we're going from positive to negative, so we need to subtract the EMF. So we're going to subtract 20 volts. Continue, this segment doesn't have anything. Now we get to this segment. We are going against the current across this resistor. So in this case, we're going to add 250 times I3. Now, we actually already know I3. It was what we solved for last time as 0.06. So we can erase that and plug in 0.06. And we know that now that we're back at our starting point, we should be at 0, so it equals 0. Now again, we only have one unknown, so we can solve this algebraically for our unknown. 250 times 0.06 is 15. 15 and negative 20 together make negative 5, so negative 125 I2 minus 5 equals 0. Now let's continue this, get I2 to the other side. Now we notice that when we solved for I2, we got a negative 0.04. As we talked about at the beginning, if this ends up being negative, it doesn't mean that there's not a current flowing, but that we assigned our arrows in the wrong direction. So instead of I2 flowing this way, our current actually flows this way. So we're going to change the arrows to flow in this other direction. Now we can use this, because our magnitude is still correct, to solve for I1. Which gives us 0.02. Now you can see how the junction rule and the loop rule, which are Kirchhoffs laws, can help us to solve our more complex circuit diagram needs.